almost what you might call a proof of concept. They've taken data from the Milky Way that they haven't been able to image the central black hole. They've got more data from a second observing ray. But now, for the first time, we're looking directly at the environment of the black hole itself. And also, if you want to do better than this, the only way we're going to build a more accurate telescope is to actually go into space. So this produces a case for space-based very long baseline. Is there any questions about this?
I had one thing not to do with the physics or anything, but I thought it was interesting when the first LIGO announcement was made, there'd been leaks on the internet in the week or two before.
Yeah.
The other, whereas this team seemed to keep it completely
They did some, I think they kept it better zipped. The one guy in particular leaked the LIGO date. I mean, lots and lots of people have heard it, but I think that there was one person who couldn't resist. Like, I've heard the story and I thought, you know, I could become Twitter famous if I and I thought, no, thousands of people have worked really hard for years to do this. I'd be at some point. What's the name? I did that, but it turned out one of my colleagues was a complete system. And he did. Yes, there's a question about it.
This is a bit off subject, but if you consider the case of primordial gravitational waves from the period of inflation,
yes,
if inflation is correct,
yes,
do the LIGO type detectors, assuming they become even more sensitive, will they be able to detect those, or do you need something completely different?
I'll get to that in a second. Actually, I wasn't going to talk about that, but since it's actually something that's close to my own heart, I can say something about it. So the one more thing that I wanted to tell you about, or what happens next, is that the next, there's a bunch of gravitational wave detectors that are similar to LIGO that are being commissioned at the moment. There's an underground one in Japan, which turns out is less sensitive to some kinds of noise. And the more detectors we have on the sky, the greater our ability to detect gravitational waves. We're to the point you might be expecting to see 1,000 merger events. But the one other one that's interesting is this one here, which is lesser, which is going to fly in space. And so this is being funded by the European Space Agency. And there's a group of New Zealand astronomers and physicists who are actually contributing to developing the analysis algorithms that will be used by LESA. It's currently talking about flying in the early 2030s, although there's some reason to think that it might fly, in fact, a little bit earlier than that. But this would actually look not at the merger of solar mass-sized black holes, the ones that LIGO sees, and operate at much larger wavelengths, and so it would actually see them when two galaxies merge. Eventually, their central black holes will merge, and so it will see the mergers of million solar mass black holes will be sensitive to those frequencies that will fly in space. In answer to your question, a slightly different version of LESA that was tuned to a slightly different frequency. If you wanted to directly observe gravitational waves that go from the Big Bang, you would most likely do it with a space-based antenna, because you can actually, it turns out they operate at frequencies that work better for that, and also you can do a better job of taking out the noise for these ones. So people are actively thinking about it. It turns out it will be somewhat smaller than LESA because you're tuning it to a different, sort of frequency of gravitational wave. But there are, it would be 20 years now, but potentially space-based interferometers would do that. Okay, so that ends my prepared comments. If anything else happens, I'm even going to have to throw something out because I'm really pushing the time limit here. But I'm happy to take questions or to chat over coffee as our chair sees fit.
I had one question. I recall a few years ago there was this detection of possible D-mode polarisation on the cosmic microwave background, which was shown to be wrong because they underestimated the amount of dust in the Milky Way, which causes a similar effect. So has any progress been made on that?
So the thing that's been asked here is that there's in fact two people have alluded to it. So processes in the very early universe can generate a bath of gravitational waves that essentially fills the universe. And so that would mean that everything in the room was kind of continually being jiggled by the gravitational waves, but their amplitude would be much lower than the occasional bursts that we see from gravitational wave emission. There was a claim, I think in 2013, that this background had in fact been detected not in a gravitational wave detector, but in terms of sort of very complicated patterns that had left on the microwave background. But it turns out what they were actually looking at was dust in the Milky Way that had interacted with the Milky Way's magnetic field and had kind of mimicked the signal that you would expect to see. There's lots of reasons why they were wrong. It's kind of embarrassing, but these things happen. So people have continued to look for that signal, but the magnitude of that signal, there's now the upper limit on it is much, much tighter than the signal that the BICEP 210 claimed to see. And so it turns out the telescope was actually beautiful. The actual data they had was much better than everybody else's. But what they had wrong was their assumptions about the amount of dust in the Milky Way. So once you corrected that, it's not a data problem, it was an analysis problem. That work is very much ongoing. And whether or not we see vast gravitational waves, we're either ruling out theories about the early universe or we're potentially finding a smoking gun, the sort of violent physics, trillionth per second after the Big Bang.
Now, I've got an elementary question about gravitational lensing. If you're treating a picture like that with a grid on it that's being warped by gravity, and say you have a beam of light or something following one of those lines that dips in near the well,
yep.
Why doesn't it dip straight out and follow straight on the line without being bent on its overall path? Why does it curve and then come out of the
So it's probably more, I mean, maybe these things are maybe a little...
I know that it's simplistic.
Yeah, I think the curving here, I mean, I think this is an artist's impression. So it's more like someone who gets, rolling a ball into a bowl or something like that, and it will be bent, and then it will come out at an angle. So it's more like a lens in that sense. So the grid lines should actually be bent in some sense. The grid, like a photon, wouldn't travel along the grid lines in this picture. Because these grids, I mean, everything is at 90 degrees to everything else as far as I can tell. But what it means is that space, once you have the deep gravitational well or gravitational wave, space has some intrinsic curvature. So it's really, it's the picture that's the problem.
Yeah, I've got a question. There's something I can't understand. You said that black holes are space. They've got nothing in them.
Yep.
And that large stars can end up being black holes.
Yep.
I can't get around the concept of how something that's just space, it's got nothing, can generate so much gravity.
So what a black hole is it's like a belly button where it's not so much a memory, it's not so much mass, it's a memory of where mass was. That almost falls out of the universe when the black hole forms. And so the space is bent and it's kind of knotted, and so it can't unflex, but the stuff itself that created the black hole has just fallen out of our universe completely. So you can fly straight through it, but the curvature, the knottedness is something that stays behind. So it's, people talk about it as like the grin on the Cheshire cat or something like that. It's the thing that produced it is gone, but the curvature stays behind.
Yeah, but why does that happen?
Why? It's a good question. It's always reminds me of dealing with small children. Well, why is the sky blue? Well, the sky's blue because blue light is scattered more than red light, and why does that happen? Well, because of quantum mechanics, son. And then you say, well, why quantum mechanics? And you say, shut up and go to bed. And so I think in that sense I guess the question that you're really asking is, why is it that the curvature of space-time is the thing that defines gravity? So to some extent,
what I'm saying is why does once the matter disappears, that stay there?
What does it curve? Well, this is I think, why is it that the Einstein's equations say it since then. So there's no way for it to relax to its, like the curvature somehow gets locked into space, even though the stuff that created, the original source of the curvature has vanished.
So but no one knows why it's like that.
I think what you're really asking is why is general relativity? Because general relativity says that it does, but we don't. Beyond why why does space behave? Why does our universe choose to work that way? We don't even know whether it has a choice.
I thought there was some wonder in black holes though.
Didn't Hawking say that there's just a trickle of radiation comes back?
So that's a
separate
problem. So in the center of a black hole is what we call the singularity, and what that really says is we don't physically understand what it is. So like if you put a star and it collapses, as soon as the star vanishes beneath its switched out radius, then the black hole would form from that point of
I
view.
thought Stephen Hawking said the mass kind of gets denser and denser, and then eventually it slowly, but very, very, very slowly, the mass kind of just.
Right. So what Hawking, or the thing that both of you are talking about is a thing called Hawking radiation. And so
Yeah.
so the idea is that if there wasn't quantum mechanics, the black hole would live forever. But because you can produce air like inside of what we call the vacuum, there are particles and antiparticles that are pairs of them that have been produced all the time, but also then find each other and annihilate. So you sort of borrow this pair of particles from the vacuum, and then you pay the vacuum back by destroying them. If you're right next to a black hole, if one of those particles crosses the event horizon, then you can't pay the vacuum back, and you're forced to create a particle. And the way you do that is by charging the black hole for the energy that you created, that you've used to create a particle outside of the black hole. I mean, this is a very waffly way of putting it, but it's some, and so what happens is, so quantum mechanics allows, the only thing that's escaped from the black hole is energy in some sense, because no physical object has escaped from the black hole for that to happen. But the black hole will slowly get smaller and smaller and
So
smaller.
you're saying like the atoms would get destroyed inside the black hole?
The instant something falls inside of a black hole, it doesn't necessarily fall apart right away. So the question of what happens to a physical object that falls into a physical black hole, we don't actually know the answer to that question. Certainly, sooner or later, it will get torn apart just because the gravitational field is, so strong. But the mathematical description of the black hole has this kind of point of infinite mass at its centre that we call the singularity, and everything else is empty space.
So would that mean that, so the protons and the neutrons would get ripped apart inside, so that it would get recycled? Because Stephen Hawking said that, well, I don't know if it was Stephen, but it goes from hydrogen to helium, and then it gets higher and higher, and it can't be reversed. So it can be reversed.
You have to put energy in to reverse it. So when you burn.
So it does reverse. So because no, what?
No, I get what you're asking. So
Yeah, because what happens? They say that once all the hydrogen is gone, once it's all been transformed into stars, then that the whole universe dies, right?
Mm-hmm.
So you're saying, like, I've been wanting to answer this for ages. You're saying that there's a possibility that the universe can actually regenerate itself because it
I see what you mean.
so it can create itself again.
So what the
or not.
universe would most likely regenerate itself as would simply be very cold, very long wavelength radiation. So
But could it reform like hydrogen and then?
not as far, very tiny amounts. So not as much, nowhere near as much as you started with, tiny billionth of a
But if
trillion.
you waited long enough, it could regenerate itself eventually, maybe.
No.
No?
You're right that, it's more, ultimately, if you waited long enough in an otherwise empty universe, a big black hole will eventually fall apart. But it will fall apart into primarily photons. And so those can't then fall, those aren't hydrogen atoms, it's just cold light in some sense.
Protons and neutrons.
Yeah, so the physical particles that you want to do that, you probably can't make. Or you probably can't get those back out of a black hole. There's not many significant numbers. Only in the very, very last stages of a black hole's decay would you be getting particles rather than just photons, things that are massless.
Another question I had was on that image of the environment of the black hole. I think I recall reading that you from the detail of it, you could determine the rotational state of the black hole, possibly.
Yeah, you can, in principle. So what happens is with a rotating black hole that's rotating rapidly kind of drags space around with it. And so the orbits close to the edge of a rapidly spinning black hole are actually quite different from what you see for a stationary black hole. And we think that most of the astrophysical black holes that we see, like actual black holes as opposed to mathematical black holes, there's reason to think that most of them are rapidly rotating. In other words, it's not only the kind of Kerr's equation is kind of a minor correction, is that you're very, very close to the black hole. You would absolutely know that you were living next to a Kerr black hole and not to a Schwarzschild black hole.
So they'd be able to determine that for the M87 black hole?
Yeah, no, it's consistent. It's not particularly well measured at this point, but it's consistent with a spinning black hole.
Without putting on the spot in terms of merging quantum mechanics and really
I don't know, I think we've already done that. You're not the first today.
Can you discuss the role of the Higgs boson, which gives mass, and gravity, which is
So no, I can sort of do that. Both things are quite different from each other. So
Yes,
the mass.
I just want you to join them together.
Do that.
Or perhaps, can I throw in a curveball of graviton? So, gravity is a field.
So okay, the graviton is kind of easier in some sense. I'll do that first. So if we have a quantum theory of light, and so that tells us that the electric force has to be carried by particles are carried. Tells us that and so in the quantum theory of light, the job of the particle that carries the electric force is the photon. And so in the quantum theory of gravity, which is entirely hypothetical, the hypothetical particle that will do that is the graviton. But we've never seen any reason for needing to have a quantum theory of gravity. It's just our belief that the universe is kind of fundamentally quantum that makes us think that there should be a theory of quantum gravity, and therefore that there should be a particle called the graviton. So that part, the graviton is hypothetical, but we know what properties would have to be, if a theory of quantum gravity existed. So that, I don't know if that answers that question, but it certainly kind of
No, that's good.
points in that direction.